Dalton's law of partial pressures deals, so to speak, mixtures of gases. In the empirical form of Dalton's law, the law is quoted as the total pressure a gas mixture is the sum of the partial pressures of each component gas of the mix. And that's kind of the verbose statement. Mathematically, this simply boils down to the total pressure, P sub T, to equal the sum of individual pressures of the gas mix from the first item you choose to however many items you have in the mixture. And this translates to, say, P1 plus pressure 2 plus, and then on up to whatever the nth number. And that's the simplicity. The mathematics sometimes looks more intimidating than it actually is. For example, if you're given, say, the partial pressure of CO2 to be 715 millimeters, the partial pressure of O2 to be 86 millimeters, and the partial pressure of, say, hydrogen gas to be 10 millimeters, what's the total pressure? Well, it's just simply the sum of those pressures, which would be pressure CO2, pressure of O2 plus pressure of H2. And that includes 715 plus 86 plus 10 millimeters of pressure, or mercury if you need to. I got 811 for the total pressure. Yeah. Now, out of Dalton's law, or associated with Dalton's law, is an issue called the mole fraction of the gas component that's within the mix. And it's like a percentage. What is the percent of that gas component in the total? And you recall, if you were wanting to get a percentage, it's part over total times 100. Well, when we talk about mole fraction, we use a symbol, capital X, that's the common symbol, of component I, individual component, will be equal to the moles of component I divided by the sum of the moles of all gases. Now, one of the elements in this is the sum of all the molar fractions always equals 1. So if you had all the percentages of a mixture, you would add them up, they'd be 100%. Well, mole fractions are not expressed in percentages. They're expressed as decimal fractions. but it's the same thing. You would add them up, they'd be 100 if they were in percent. And mole fractions being decimals always add up to 1. So, in the condensed format, Ni over sum of n is really what the textbooks would show you, from I equal 1 to n, sum of all the individual, like that. Now, where does this come into play with Dalton's law? Well, when we're talking about moles, we're talking about using the ideal gas law. So from the ideal gas law, we see PV equals nRT. We find N equals PV over RT. And so that is related to the ideal gas law in this relationship. Now, if it's an individual component, that would be related to the individual components. Now, if you're talking about the moles, the total moles of the mixture, that would be those subscripts would be totals, like PV equals nRT totals. Not there. Total moles, total temperature, like that. And N total would be PV over RT total, like that. So mole fraction now, I'm going to drop Ni over N total is equal to PV over RTI, PI VI over RTI. So there's one of them. And you have P total, volume total, R, and temperature total. So you can see that these were derived, each one of those derived from the ideal gas law. Now, when we're talking about a mixture of gases, I'll do it over here. You got a mixture of gases, no matter how many you have in there, what can we say about the volume for each of the gases? It is always the same. All of them are occupying whatever volume the flask is. So what happens is the volume occupied by individual gas here, the red dots, is the same as the volume occupied by everybody. So it's, you don't have any distinction for individual component gases having, well, that has a certain volume. No, they all are in the same vessel. Also, R value is, of course, constant, and you can cancel that out. And then if the temperature of the red dots is, 273, what are all the rest of them? Well, it's the same. So temperature drops out. So you're only left with two terms now, the individual partial pressure and the total pressure. So that's PI over pressure total. Now, what I'm trying to do is show you where all this comes from, but what you will use from a practical standpoint is mole fraction I equals N mole fraction of the individual mole of the individual component of the total moles is equal to partial pressure over total pressure. Total pressure there. So this is your kind of a working equation for solving a lot of the problems that you will run into in gas laws. And they see some real good ones in the Ebbing text. But anyway, let's work a few and see how we use this little set of formulas right here. And may or may not use all of it. Okay, I'm going now to the set of problems, the Dalton law problems, and we'll see how it works out and see how it fits in what I've just given you. A metal tank contains 3 gases. Oxygen, helium, and nitrogen. Of course, those will be molecular forms, like that. The partial pressures of the 3 gases are 35, 5, and 25. 35, 5, and 25, and they got them in atmospheres. What's the total pressure in the tank? Well, the pressure total, as you recall, is the sum of the individual pressures. Pressure of O2 plus the pressure of He plus the pressure of molecular nitrogen, which would be 35 plus 5 plus 25 atmospheres. And it's that simple, guys. Nothing there. Now, some of the problems can get real gnarly, and especially when we get to chapter on colligative properties, chapter 12, where we're talking about solution vapor pressures and mixtures. So in this one, the answer is 65 atmospheres total pressure. Okay. So here, a blast furnace gives off an unpleasant, unhealthy gases. If the total air pressure, and number 2, pressure total in this blast furnace is equal to 0.99 atmospheres. The partial pressure of carbon dioxide is 0.05 atmospheres. And partial for hydrogen sulfide is 0.02 atmospheres. What's the partial pressure of the remaining air? Okay, so this is total air pressure, which happens to be the sum of all of the individual pressures. So the question is remaining air. Is your central question. So it would be the total pressure to equal pressure of the CO2 plus pressure of H2S plus the pressure of whatever the remaining air is, substituting 0.99, 0.05 atmospheres. 0.02 atmospheres and the pressure of the air. Solving for the pressure of the air, that would be 0.99 minus 0.05 minus 0.02, and it finishes in atmospheres. A gas mix contains 2 moles hydrogen gas, 3 moles ammonia, 4 moles CO2. And 5 moles of N2. And together, the total pressure is 800 millimeters of mercury. What's the partial pressure of each gas? Pretty straightforward once you see how it's put together. And this problem will give you a good idea of what we're talking about relative to mole fractions. Okay, so the first thing that is needed is the mole fraction of each one of these components. And the mole fraction is part over total times 100. So if I add up the total moles is 2 plus 3 plus 4 plus 5 moles. 5, 9, 10, 11, 12, 13, 14 moles for the total. So if I want the mole fraction X for H2, it would be 2 parts out of 14, part over total. Okay? So that'd be 2 over 14. Mole fractions do not have units. It's like a percentage. It's just that fraction of it. Mole fraction of ammonia is 3 out of 14. The mole fraction of the CO2 is part over total, 4 out of 14. And the mole fraction of N2 is 5 out of 14. So you can see them. I got for each of these. Now, the sum of the mole fractions will be 0.142, just checking to be sure we're correct, 0.2143 plus 0.2857 plus 0.3571. So it confirms that our calculations of mole fractions up here, if you were to convert these into percentages, this would simply say this would be 14, the mixture is 14.29% of H2, 21.43% ammonia, 28.57% of CO2, or 35.71% of the nitrogen. Does that make sense to you guys? That's what a mole fraction is. It's just a percentage, but it's expressed in a decimal fraction form. Now, if you have a total pressure, now listen to what I'm saying. We've got a total pressure of 800 millimeters. Each component exerts its fractional pressure contribution of that 800. For example, you have 0.1429 of the 800 is the H2 pressure. 0.2143 of the 800 is the ammonia pressure. See what I'm saying? It's just that fraction of the total, and that's how you do it. So if something was 10% of 5,000, you take 10% of 5,000, and that's what would represent. Well, the same thing here. So in calculating the partial pressures of each one, we'll start with hydrogen. Hydrogen was 0.1429, fraction of 800 millimeters of mercury. And then the partial pressure of ammonia equals, where's my number, 0.2143 of 800 millimeters of mercury. And the partial pressure of CO2 now is 0.2857 times 800. And the partial pressure of nitrogen is 0.3571 times 800. And then you go through and multiply out. And if you add them up to check, you will get 800. This is what I got. And that's the answer to the problem. But the essence of this is we calculated mole fraction. And if you have a mixture of gases and you know the total pressure, and you know that now how to get the mole fraction, so mole fraction times total pressure gives you the individual mixture components pressure. And many problems in chemistry and physics, if you're working in that area, are always in a mixture kind of format. And so hopefully this will give you some insight into how to deal with that. Please jot that down, and it's very straightforward if you compare it with what we've just done. The gases are given in grams. Well, what does that tell you? It tells you to first need to convert to moles, and then once you get each one of these into moles, then add up the moles, and there's your denominator, and then you can get each mole fraction. And then you're given the total pressure down here. So the mole fraction of each component times the total pressure will give you each component's partial pressure. Just what we did. The only twist is, in the previous problem you were given moles, in this problem you're given grams and have to convert to moles. So that's what the deal is. Everybody good? Make sense? Please ask if you doesn't.